So, good morning. Today we'll talk about persistent data structures. Okay, so what is a persistent data structure? A persistent data structure is a data structure, so it's a modification of some standard data structure like a segment tree or a Cartesian tree or maybe a queue that can in some way access the past. So we have some data structure. We can look at it as a black box for now. And what we do is usually we make some queries to it. So we either add some elements into it or we, add X to all items in a range like we do with a segment tree. Anyway, we get a sequence of versions of data structure. And usually, in a normal data structure like a STD set or a segment tree, we can only look at and we can only modify the latest version. While in persistent data structure, if we make some data structure persistent, well, there are options. So there are 4 types of persistence, but we will usually be only concerned with the first 2. So the first one is a partial persistence. So whenever we have a partially persistent data structure, this means that we can only modify the latest version, but we can access all the previous versions. So we can modify. So basically the timeline for the life of our data structure looks like a line, right? So we have some initial, maybe it's an empty tree, maybe it's an array of zeros. Then we can add something, we can add something, we can add something. We can always add something to the latest version. So we can only create a new version here. But depending on the data structure, we can hopefully effectively access any of the previous versions. And the second type that we will be concerned about is full persistence, where we can modify the latest, modify any version, so we can branch out at any position, and well, and still we can access any version. So it's full persistence. Okay, so there are 2 more. Well, the one is concerned with whether we have 2 different structures and, for example, we can concatenate them or we can take the union of 2 sets. Yes? So, and the last one is called function. Okay, so first of all, why do we need persistent data structures? Well, usually in complex problems, we need them because we have what's called online problems. Usually, most of the problems you see are offline, so you can read all the input data and you can process the input data as you like. So, for example, if you have queries on segments, you can sort all segments by the left border and process them in that order. And sometimes it's easier than to just process queries one by one. And in online problems, you are usually forced to process queries as they come. And then offline, of course, is where you have all the input data right from the start, and you can sort the queries, or you can calculate something and build a compressed segment tree, for example, on those queries, and so on. So usually, when you have online problems, the persistent data structure is your choice. So you act like if you were solving an offline problem, then you make the data structure that you're using persistent. So now you're using, and now whenever you have some queries, you can ask some versions of your data structure, some versions of your segment tree or a Cartesian tree from the past, and then act like it was an offline problem, but now it's online. So that's the main use. But sometimes online problems arise on their own. So for example, when you do a binary search, then you need to, well, on each step you have to make a decision, right? So you calculate the sum on the segment, and you either go left or right, for example. And sometimes you need all the versions of the segment tree. Okay, so we'll look at some problems that are solvable with segment tree and Cartesian tree, but after we learn what they are. So, okay, so first of all, let's talk about some easy data structures, like stack and queue. Well, the persistent stack, a fully persistent stack, is a data structure. So, suppose we implement stack as on structures. So each node of the stack is a structure, and it has some value. So this is the bottom of the stack, and this is another node, this is another node, this has value 5 and points to this node. So basically each structure has two fields and points to the value right below it. So this is the top of the stack. Okay, so for a stack, we would like to somehow maintain all possible versions, all previous versions, and be able to modify them. Well, what is the version of a stack? Well, a version is, well, a sequence of values, right? So if this is 5, this is 8, this is 2, then we have a stack 2, 5, 8, 2. And the top of the stack is 2. So what if we want to insert one more value? Well, we create a new node, for example 4, and let it point to the old top, and this is the new top. So now we have basically two versions. This is the first version, and this is the second version. Okay. What if we want to take this version and add 9 instead? Well, we can take this top and again create a new node that points to that top. So this is the version 1, this is the version 2, and this will be the version 3. So we have 9 that points to the same top as before. 1, 2, and 3. Okay, so what if we want to create a new version? Again, we want to take this version and remove the top from the stack. Well, removing the top from the stack is just the same as moving the top of the stack to the parent top. So 2 was the previous top, and it points to 8. So now the new top will be 8. So this is the version 4. And now we can add something to version 4. For example, we can add 3 to version 4. So we create a new node here. And this will be the version 5. And so on. So basically maintaining a fully persistent stack is just the same as maintaining a rooted tree. Okay, so how do we deal with a queue? Well, we can try to do something similar. Right, so we maintain the head and the tail. And now, for example, to remove an element from the head, this is just a new pair of new head here, head prime here, and tail prime here. So this will be the second version. But what if we want to add an element to the tail? Well, we cannot just simply modify this node, right? Because if we add one more node here, the old versions are now corrupted. So the old versions now think there's an element after tail, but there is not. And so if we want to add one more element after this one, we'll have to basically maintain 2 links out of the last element here. So if we want to add 2 different elements to the initial version, then we'll have to have 2 different links, and that's not possible. Well, that is possible, but this doesn't make this data structure efficient, right? So, by the way, the easiest implementation of a fully persistent data structure is just copy and write data structures. So whenever you need to make a modification, you can just copy everything you have and make that modification. This is, of course, not efficient, but one of the possible implementations of that. Copy and write data structures are heavily used in concurrent programming, since you have some problems with simultaneous access to data, and if you copy every time you change something, there will be no race conditions. Not really no race conditions, there are still intricacies with that, but the idea that is if you read a lot and you change small number of values, then you can just copy it every time you change something. Would be a fine implementation of that. Okay, so the queue is not that easy. Okay, let me tell you about one more implementation of the queue that uses 2 stacks. Some of you might be familiar. queue with 2 stacks. Okay, so turns out we can simulate a queue with 2 stacks. Well, we'll have one in first stack and the second stack. We'll call the first stack an input stack, and the second stack the output stack. So we'll have some elements in the first stack, and we'll have some elements in the second stack. So whenever we want to add an element to the tail, we put it on to the first stack. Whenever we want to dequeue an element, whenever we want to pull an element from the queue's head, we'll take it out from output. And there is only one problem: when this becomes empty. Okay, so when on the dequeue operation, if out is empty, well, for example, in the beginning of the problem, so you inserted some elements into in, but there were no elements into out, so the out was empty. So if out is empty, then we will move all elements from in to out one by one. So if there are some elements in the in stack, 5, 4, 1, 2, and the out is empty, move all elements from in to out. So we'll move all elements one by one. So first we move 2, then we move 1, then 4, then 5. So now the input stack is empty and the output stack contains 2, 1, 4, 5. And that's good, because whenever we take an element from the output stack, this will be the first element that was put in the second stack, and this way we maintain the first in, first out. Right? So the element 5 was put before all these 4, and whenever we want to dequeue an element, we will put this one out. So, and this works in amortized constant time because, well, each element is put exactly once in the input stack, then moved exactly once from in to out, and we pull it from out exactly once. So there are 3 operations with stacks for each element. Well, turns out, well, and we know how to do persistent stack, so we might say that persistent queue is just these 2 stacks. Is there any problem with that? The problem is in the word amortized. So the word amortized ruins everything. Since if there is an operation that works, that takes a long time, then we can create a data structure that the next operation will take a long time. So we have some data structure. For example, we put a lot of elements into the input stack, and then we take one element out of this queue. So suppose this operation takes data of n time. But now we want to modify all the previous versions. So we can do the same operation, and this again will take linear time, and so on and so on. So basically we can create a state such that the next operation is bad in real-time sense, but in amortized sense it's still constant. And this way, we get that the real time or even the amortized time for our persistent data structure is still too large. So the basic rule is whenever you have an amortized operation, whenever you have an amortized running time of your operation, this usually doesn't work with persistent data structures. Sometimes it does, but usually it does. There is still a way to implement a persistent queue or even a persistent deck, but the algorithms for that are harder. And, well, I can explain in not a lot of details how the persistent queue using the same principle works. Well, we cannot do it with two stacks. Well, it turns out if we allow a little bit more stacks, then we will still be able to do it. So it's possible to implement queue with stacks in real constant time, but with more stacks. So the basic idea is, okay, so while we do operations, let's have two stacks. And for each operation, let's move two elements from the input stack to output stack. So whenever we do some operation with these two stacks, we will have two more, the input and the output stack, and we move two elements to the output stack. So basically, we're delaying those operations. We're not delaying those operations, but we'll have to do them with different stacks this time. So that's the basic idea of how this works. You can read it somewhere. Yes?
I think, I can't remember correctly, but I think that you can implement queue with persistent addition tree, right?
Persistent what? Sorry?
Addition tree.
Yes, yes. We'll talk about more complicated data structures right now. Yes? Okay, so let's talk about segment tree. So let me draw a segment tree for an array of 4 elements. So we have 4 elements at the bottom. So we have 2 more elements on the next layer and 1 element for the root. Well, the exact operation here doesn't matter, but we can think that it may be a sum of all elements in the subtree. So for example, here 3 minus 1, 2, 5. So here the sum is 7, here the sum is 2, and the total sum is 9. So what happens when we modify these 2, for example? So we want to change these 2 into the minus 2. Okay, so the good rule of thumb to when you implement persistent data structure is, first of all, you don't use arrays. So an array is such a data structure where it's not really, well, it is possible to make it persistent, but this will be just the same as the segment tree. So, and the data structure that can be implemented with pointers are the better choice when you implement persistent data structures. So use pointer-based data structures. So this will mean that our segment tree will not be based on the array, but instead will be based on this tree-like structure. So we have a node and we have a links to the left child and the right child. Pointer-based structures. So since we use structs, basically, the second is make all your structs immutable. So whenever you create some node for the second segment tree or for a Cartesian tree or for a stack, try to make sure that this node is immutable. So you'll try to never change values. Whenever you need to change some value, you will usually create a copy of that node with a new value. That's usually how persistent data structures work. Make fields immutable. So, and if all of the fields are immutable and you never change them, and instead to change some value, you create a new node with the new value, and if all the fields are immutable, then it's harder for you to accidentally corrupt some version, and so if you never change them, all the old versions are correct, and the new versions are created by just copying some of the old nodes and creating them. So we'll use this paradigm for now. There is another paradigm, but we'll use the copy nodes technique for now. So we want to change this, right? So we want to change this 2 into -2. We cannot change this value here because the initial version will be corrupted. So instead we'll create a new node -2. And we'll say that, okay, all the nodes except for this one will be the same, and this will be -2. Well, since this node changed in this version, which nodes need to know about this change? Well, we have a parent of this node, so we have this 7 that first has a link to that node. Second, calculates the sum that involves this node. So we need to communicate this change to this node, and again, we will create a new node. The value for that node will be 3. Its left child will be this new node. And what is the right child? The same node here, right? So this node didn't change, so we can just put the old link to this node. Okay, now this node has changed, and the root needs to know about that the right child of the new root has changed. So we create a new root. The value for that root will be 5. Its right child is the copy of the 7 node that became 3, and the left child is the same as the old left subtree. So basically, if we now do a DFS from this tree, so we'll have 5 here, and we have 2, 3 minus 1 here, and on the right we have 3 minus 2 here and 5 here. So now if we run DFS from this new root, then this will correspond to the new segment tree with the element 2 changed to minus 2, but we only added 3 new nodes instead of copying all 7 nodes. So this means that, by the way, usually we will address to the version as to the root. So in persistent segment tree, the version is the same as pointer to the root. So this is the version 0, this is the version 1, and usually when we work with persistent segment tree, we'll just store them in the vector. So we'll have a vector of different versions, and to take any particular version, we'll just find the corresponding root, and we'll do the query to that root. So let's change some more. So if we change an element -1 to 4, for example, so this element gets changed. So it's 4. Now we have to copy this vertex. So this is now 7. And the left child is way back here. And now we create a new root. So notice that the root is always changing. So every change in any leaf affects the root. So we can just find any. So basically the change in any leaf propagates to the root, and we'll always have a new root. And that's why the version is the same as the root. Now we have 7 here. We have 7 here. So the new root is 14. Right? Well, no. The left subtree is 7, but the right subtree is 3. So the new root will be 10. The left child is this one, and the right child is here. So it might become difficult to follow these links, especially from a couple more operations. But on each operation, when we modify some leaf, we will copy all the nodes from the path from this leaf to the root. And the new root will correspond to the new version. So the runtime is still the same. So if an operation worked in log n time, this will still work in log n time. But the usual problem with persistent data structure is memory, not the time. Well, the time is a problem too, but usually in practice you have more problems with memory, because in normal segment tree you will always create a new node. You won't create new nodes, so you will have linear memory but log n time per query. Here you'll have log n additional memory per query. So you copy all the log n nodes on the way to the root. So additional memory. This, by the way, usually sometimes can hint at the solution with persistent data structure. So, for example, if all problems have memory limits 256 megabytes, and this problem for some reason has 1 gigabyte, then it might indicate that the intended solution uses more memory than usual, and the persistent data structures are the ones that use more memory. Okay, so how do we implement this? So usually all these pointer-like structures will return the new copy of the object. So let's implement this. So I'll return the pointer to the node, and so for this operation, so set some index of the array to some value. Set. So we have the current node, the pointer to the current node. We have the current. I don't know how you implement segment trees, but usually you pass the current left border and the current right border. So int left, int right, and two more values: the index and the value. So, if you are already at the leaf, so I usually use, by the way, and I recommend you to use half intervals, but that doesn't really matter. So, if L plus 1 is R, so this will work as follows. So we will create a new copy of the leaf with the new value. Return. New node. Let's do it like this. So create new node. Well, we create a copy of the current node, but with the new value. And then return the pointer to that one. So, what if we are at some branch? So we know that we're here, we have the left subtree, now we have the right subtree. First we figure out where do we go, then we create a copy of the current node with the new left pointer, with the new left child or the new right child, and then return the copy of that node. So we figure out where do we go, so we calculate the middle value. We figure out where we go. So if index less than m something else something. So after we did the recursive call, we collect the new left pointer or the new right pointer, and we assemble the copy of that node. So maybe the right subtree is the same, the left subtree is the same, but the right subtree is a new one. And we return it, and this way we'll propagate back to the root. Notice that you don't need to store parent links here. Right, so usually in tree structures, when you're trying to make a tree persistent, you need to avoid using parent links, since this technique of making a data structure persistent doesn't really work well with cycles, right? So, for example, if this node also had the pointer to the root, so we change this node has to know about this change, so we change this, so we copy this node, but this has to know about its parent, so we need to copy this again, and so on. So this version, copying, I think it's called node copying, so it doesn't work well with cycles. By the way, range queries are the same, and we just do the same like recursive descent from the root to the nodes that we need to modify, and each time we modify a node, we copy it entirely. And if you do it carefully, so use delayed operations on the segment tree, this will work fine. Okay, so let's take a look at the example of a problem that can be solved using persistent segment tree. So first, any problem that is online and requires you to use a segment tree can be solved with persistent segment trees. Let's look at a couple of examples. Yes?
Repeat about range updates.
Well, what do you do in range updates, right? So in range updates, you usually have like a three-step program, right? So you have some query from L to R and something else. So first of all, you push updates to the children. Push updates to children. Second, you make recursive calls where you need to. Or maybe just one recursive call. And third, you finish processing all the recursive stuff, and then you just find what is the then you basically recalculate all the values in the current node, right? Recalculate current node. So all these three operations can be done if all your fields are immutable. So first you push updates to children, but you only push them to children, not to children's children, right? So if you have some delayed operation in your current node, so for example here, you remember that you need to do +5 to all the children. Instead, you add the delayed operation here and delayed operation here, and you copy these nodes if necessary. Then you make recursive calls, and this, well, you had the old node, then you made the copy to the node that has this delayed operation +5, then you had some other copy that was returned by the recursive call. So this will be your new left child, and so on. And the same with the right part. So you had some initial right child, so then you make right child with the delayed operation +5, then you make recursive call here. Maybe you create a new copy of that vertex without this +5 because you push this operation further down. Then you create this node, and this will be your right. So basically, all the nodes that hang from the nodes that we visit during the normal segment tree call will be copied here. So still we visit in order of log n nodes in normal segment tree call, so at most twice that amount here. Well, usually smaller, right? Usually the structure of your segment tree, and you can make some tricks to not create intermediate versions. So you have to be careful. Like you either have to make your fields non-immutable, but be really careful with what you modify. So you only modify it during the intermediate stages. So basically you don't need this intermediate copy, right? So you can avoid creating it, thus you'll have less memory to worry about. And we'll talk more about memory when we'll talk about Cartesian tree. So there are more memory problems with Cartesian tree than the segment tree, usually, because it has higher constants. Okay. So there are 3 steps, and all of them can be done with just copying constant number of nodes here. And you have to be careful to, well, if you do this mistake, your normal segment tree doesn't work. Like if you push updates to children, then to children's children, then to children's children's children, then your segment tree works in linear time. And if it doesn't, so you have to only push these delayed operations to the next level, then you should be fine. Okay, so let's talk about another problem, which is, well, let's calculate all the number of distinct values on a segment. So we have an array. Okay. And the number of queries, some queries. The kind, what is the number of distinct values on the segment from L to R? Queries, number of distinct values L to R. Or maybe, I don't know, the largest unique value. So if you solved this problem using the offline, so let's first come up with an offline solution. Okay, so we have this array or number line, and we have some queries. Let's sort all the queries by the right part. Sort queries by the right border. So first we consider this segment, then we'll consider this segment and this segment. Let's say it's a larger one. Then we consider this segment and so on. So this would be the first one, second one, third one, fourth one, fifth one, and so on. So basically we move from left to right. So we add elements to the array one by one. For R from 1 to n. We add AR and then process all queries. with that right border, with I equal to R. Well, what is the data structure that we need? Well, let's have an array of zeros and ones. And there is a 1 if, so AI, not AI, let's say TI is equal to 1 if AI is the rightmost occurrence of this value. So if we have some number of 5s here, so this all positions will contain, and this is our current border R. So maybe there are some 5s after this right border, but we don't care. So there is this right border R, and in the segment tree, we'll store 0 if it's not the rightmost value, so if there is the same value to the right, and we will store 1 if it's the rightmost occurrence of AI. So now, answering the query is easy. It's just the sum of all values on the segment. Right? So all the unique values will be counted exactly once, and all the values that are repeated, well, among all the repeated values, so if we query somewhere here, so we will not count this 5 at all. We will not count this 5 because it's not the rightmost, and we will count this 5 because it's the rightmost. So for each value, we will add 1s if it's present on the segment and add 0 if it's not. So, and adding one element is 2 operations with the segment tree. We need to, so if we add one more 5 here, we'll have to make this 1 into 0, and we'll have this into 1. So here is the new right border. So we have to make 0 the last occurrence of this newly added value, and we'll have to make this the right value equal to 1. And if the problem is online, we can do the same. So we can simulate this process, and we will save all the versions of the tree. So we'll have n different versions of the tree. We'll save all of them. So add AR, then save the version into the vector of pointers to roots, for example. Save the version. And we will process all the queries later. So now, when we have a query from L to R, L to R, we take this version of the segment tree, and we take the sum of all values from L to R on that segment tree. So that's the basic example of how you transition from an offline problem to an online problem. Yes?
How do you manage updates?
You don't have updates to the array. Right? So the array is constant, and you only need to answer queries. What is the number of different values? Managing updates is hard. I don't know of a polylog solution to that. Maybe there is a square root decomposition that can solve updates, but I'm not sure. Okay, and another problem that does not, well, it still has an online component, but it has one more cool trick associated with segment trees. So you probably all know what a kth order statistic is. Right? So basically, if you have a C++ function kth element that can find what would be the kth element in the sorted array without sorting it. So you cannot sort in linear time, but you can find the kth order statistic in linear time. Let's do that on subsegments. So you have an array. Again, this array doesn't change. And queries. Find KI's order statistic. On subsegment from Li to Rl. And turns out we can do that in log n time. And of course, all queries are online. By the way, usually the online is implemented either through interactive queries, so you have to submit your answer to the previous query before you get the next one, or the next query is somehow decoded using the answer to the previous query. So you calculate the answer to the first query, using that answer you decode the second query, and so on. So these are two most common techniques to force online. There are also graders that will do queries to your class or your struct. Okay, so let's gradually solve it first in log cube n, then log squared n, then log n. Okay, so how would I find the kth order statistic on a subsegment? Let's sort all values and add them to this. I can consider this array to be a permutation. If it's not a permutation, then I can compress values and just uncompress them when I print the answer. So I can assume that this is a permutation. If not, compress. And let's add all elements in order of their increasing value. So if I have array 5, 1, 4, 3, 2, I'll have a segment tree with 5 elements. So initially it's all zeros. Then I add 1, so I get 1, 0, 0, 1, 0, 0, 0. Then I add this 2, then I get 1, 0, 0, 1. Then I add 3, 4, and 5. Okay, so how does this help? So I'll use persistent segment tree so I can store all these versions efficiently. Store in persistent segment tree. Okay, so how would I answer the query? So usually the kth order statistics is done in 2 steps. First, we binary search on the value. Then we would like to somehow calculate what is the number of values that are less than or equal to x on that subsegment, for example. Number of values less than or equal to x. If it's at least k, then this means that this x was too large, and if it's less than k, then this x was too small. If it's at least k, we need to try lower x. And if it's less than k, try higher. And already this is a solution in log squared, right? So we have our online query, we run binary search, then we have this value x. We can calculate what is the number of values on the segment from L to R, where this okay, so we have this x. So for example, if x is 3, we use this version. And we calculate the number of values less than or equal to 3 on that subsegment, and it's just the sum on that subsegment. Right? So we can solve that problem in log squared. Well, turns out that we can do faster, but we will need to use a little bit different persistent segment tree. Okay, so instead of adding values in order of the increasing value, we will add values just from left to right, and this will store values instead of indices. So these 5 elements now correspond to values or from 1 to 5 rather than indices of the array from 0 to n. This basically corresponds to the fact that if you have binary search, then a tree query, then a segment tree query, or a Fenwick tree, or a tree, usually you can combine them into one single descent on a tree. Usually the combination of binary search on some value, then making a tree query, usually means that you can combine them in some way. Since, like, descending from a tree, you already do some kind of binary search already, and usually you can combine these two into just one single descent from a tree. Not always, but it is common to happen like this. So again, we have the same array. And then we will add values from left to right. So first of all, we add the value on the 5th position. So initially we have 5 zeros. Then we have 1 in the last position. Then we have 1 in the first position. And so on. So basically for each right border, we have a segment tree that corresponds to that right position. Well, what is the segment tree that corresponds to the subsegment? I would like the I would like to efficiently for my query that I have a query from Li to Ri. I would like to efficiently get the segment tree for that subsegment. Well, turns out that if we have this subsegment, for example, from 1 to 3, it's the difference of two versions. Right? So it's the difference of this version. So it's, let's call them T0, T1, 3, 2, 3, 3, 3, 4, and 3, 5. So the tree that corresponds to these three values is just 3, 4 minus 3, 1. Right? So 1, 0, 1, 1, 1 minus 0, 0, 0, 0, 1 is just 1, 0, 1, 1. Right, so it corresponds to, well, basically this gives us a set of values that appear on that segment. So we have 1, 3, and 4. 1, 3, and 4. And we only care about those values. So this means that basically we can take two different versions of this tree and use a recursive descent simultaneously looking at some node of T4 and looking at some node of T1. So again, this segment tree will calculate sums on segments. This stores sums. And the solution will look like this. So let me draw two segment trees with 5 elements. So notice that they have the same structure, right? So the segment tree has a static structure that doesn't change if you do some queries. So these two segment trees, T1 and T4, will have the exact same shape. Well, maybe not this shape, depending on your implementation and how you round up or down your indices. But something look like this. So T1 will look like this. So these are all zeros. And this is 1, 1, 1, 0, 0. And this will look like 0, 1, 0, 1, 1, 1. This is 2, this is 1, this is 2, this is 4. So now we would like to do some kind of binary search. So if you know how to do binary search in a tree, this is basically a single descent. So first we have 2 pointers to roots, and we would like to know, is x, so we're now from 1 to 5, and we would like to know, is x, which is the result of this query, in from 1 to 3. So how do we do that? Well, we need to find the number of values present from 1 to 3. So let's say that we have L equals to 2, R equals to 4, and K equals to 2. So we would like to find the second number. So we would like to find this 3 here. So how do we tell if the x is from 1 to 3? Well, is the answer from 1 to 3? Well, we need to count the number of values on that segment that have value from 1 to 3. And if it's at least 2, then the answer is somewhere there. And if it's less than 2, we need to go to the right subtree. So it's the same single tree descent, but we now have two trees and we're moving down simultaneously on two trees. Okay, so what is the number of values on the segment from 2 to 4 that have value from 1 to 3? Well, it's 2 minus 0. So we look at the left child here and the left child here. It's 2 minus 0. So the number of values from 1 to 3 is 2 minus 0. Which is 2, and k is equal to 2. That means that the kth order statistic is somewhere in the left tree. So now we will move down to the left. So here and here. Again, our current working segment is from 1 to 3, and we would like to check. Well, is x from 1 to 2? To do that, we would like to count the number of values in the left subtree here minus the left subtree here. It's 1. 1 minus 0. Well, 1 minus 0 is 1, right? So this means that we have, well, we know that the answer is some value from 1 to 3, and there is only one number from 1 to 2. That means that we should go to the right. In this case, we decrease k, but by what we skipped on the left. K minus equal 1. And then we have our working segment from 3 to 3. And since we're at the leaf, we know that the 3 is the answer. So for example, if k was equal to 3 in the beginning, what we would do is, okay, so we calculate 2 here and 0 here. We know that the number of values less than or equal to 3 is 2. And that's not enough. We're looking for a third number, and there are two numbers from 1 to 3. That means that our answer must be from 4 to 5. So now our current working segment is from 4 to 5, and we move to the right instead of to the left. And then we do the same. We look at the left subtree here. We get that the number of values from 4 to 4 is 1. And that's what we need. Right? So we skipped two numbers from 1 to 3. And now we're finding the first number in subsegment from 4 to 5. So I think this is a really cool application of persistent segment trees, and there is a solution with segment trees that allows you to also modify values, but now the solution will work in log cube n or square root of n, depending on what you use. But if there are no changes, and that's usually the case when you're trying to apply persistent data structures or persistent segment tree, usually you have no changes, so you can build all the persistent segment trees in the beginning, and then you use them to solve your queries. Okay, so let's make a 10-minute break, and we'll be back with persistent trees and other data structures.
they went in the direction of like V times and I checked that segment intercepted with V. It works, but it's not accepted, but I had to use it on
There is a solution without any equation.
like the direction that but you know there's no solution for simplifying the
You can calculate, you can basically just apply it.
just take the second right side of the second.
Or you can write a arbitrary equation. When you're looking for solutions where you can the segment is parameterized with -1. The offline is parameterized well, this basically corresponds to choosing some point on the segment and choosing some point on the offline. Oh, these are two equations, right? There is equation for x. This is one point equation. What is this one? This one corresponds to 2. Okay, so let's continue. first, well, I promise that we'll start with Cartesian trees, but instead, let's discuss one more way to make persistent data structures. Okay, well, to make data structure persistent, which is called let's call it change list. So before we had all the fields in all of our structures were immutable. So if we wanted to, if we had some fields, some are values, some are pointers to other structures. So for example, if this was copied, that we also had to copy this, where all the fields are the same, but this one now points here. Okay, so what if we wouldn't want to do that? And instead, for each field, we'll now have basically the log of all changes that happen to that field. So we have for each field, we have a log of changes. Now, and it would look something like this. So basically, it's a list of pairs where we have value. So during version 1, this value was 5. Then on version 6, this became 2. Then on version 8, it became -2. Then on version 10, it became 5 again. Then to find the real value, of that field, we have to do binary search. I think this is called fat nodes, if I remember now. So nodes now store a lot of different values for a lot of changes. So to access some field during some version, for example, at version 7, we'll have to find this log entry. So we need to do binary search on the version, and we'll need to find 6. So sadly, this only works for partial persistence, since we don't have an easy way to insert versions inside this list. So if we can only modify the latest version, this will mean that in each log, entries will only be appended to the end, and we can easily do a binary search. But if they are inserted in somewhere in the middle, first of all, we can't really know where to insert. Then we need to maintain the tree of versions, which is a lot harder. So fat nodes, we don't copy, which is a good thing. But now we have binary search. So not only we store additional memory for each change, but we also need to do binary search every time we access some field. So we get a log n multiplier. Well, log the number of versions multiplier for our data structure. Well, looks like it's useless, so only can be easily applied to partial persistence and has an additional log n multiplier. So not only we have more memory, but we also consume more time. Turns out that if we combine these two methods, So fat node plus node copying. So if we don't allow these logs to grow infinitely large, so if we set an upper bound, so we can make any data structure into a partial persistent one. With constant overhead. Or operation. Well, node copying didn't really work because there could be cycles, and if there are cycles, node copying just doesn't work. And fat nodes work with cycles pretty fine. So if you have cycles, you just add an entry here, add an entry here, and it's all fine. Well, it turns out if we combine these two methods, then we can have constant overhead. And there is one restriction that in degree of each node must be constant. So there cannot be a node with a lot of links to it. So for example, any trees work, right? So for any trees, we have just one in degree for any vertex that's not root, and the root is a special vertex. So any vertex except the root has the in degree 1, and root doesn't have any. So if you implemented some data structure and the incoming degree of each vertex, so the number of other structures that point to that structure is constant, so that means that we can achieve constant overhead per operation and also have cycles. So node copying achieves constant overhead, right? So since for each operation we do some constant amount of new work, we get additional memory, but that pretty much counts as constant overhead. And fat nodes allows us to work with cycles too. Okay, so let's move to Cartesian trees, persistent ones. Trees or trees. So let me quickly remind you what Cartesian trees do. So a Cartesian tree is it's a binary, either a binary search tree or a way to store a sequence. So if it's a BST, binary search tree, then each node has a key value and a priority value. X is key and Y is a priority. And if we only look at X's, so if we only look at keys, then this forms a binary search tree. So we have a root node, everything on the left is less than the root, and everything on the right is greater than the root. And if we look at Y's, or priorities, this forms a heap. So this is the minimum value. In. And all the x's here, less than x here. And all the x's on the right are greater than this x here. So turns out that if all x's and all y's are different, this tree is unique. And if we choose y's randomly, and we have x's, so if we choose y priorities randomly, then this means that the expected depth of this tree is log n, so all the operations we can do with these trees will work in big O of log n time. Or this can be a way to store a sequence. So suppose we have an array x1, x2, xn. Well, not x, let's say it's a. A1, A2, an, any sequence. And we can make following operations. So we can split the sequence anywhere. We can merge two different sequences into one. We can, for example, reverse a sequence, and so on. So different types of operations with sequences. We can do all the same operations that we can with segment tree. So for example, we can change elements, or we can make delayed operations such that we add x to all elements in a subsegment, and so on. So this supports I think all of the operations that a segment tree supports, but it's a bit harder to implement, and it has a larger constant overhead. So you are more likely to get a time limit exceeded. But this allows us for larger set of operations, such that we can insert some element in the middle, or we can remove an element, or we can concatenate two different sequences, or we can reverse a subsegment, and so on. So this is usually referred as implicit tree. Since there are no keys, so we got rid of keys, and instead of working with actual keys, we'll just work with sequences, or we'll work with sizes. Since usually we need sizes anyway, so creating an implicit tree doesn't make our work a lot harder. Usually we need sizes anyway when we work with BSTs. So the way to make trees persistent is pretty much the same. So all of your operations that modify a field, instead we'll copy a node of the tree and create a new menu. So for example, let's write how merge works. So node pointed to node merge of two trees that are also represented by a pointer to the root, T1 and T2. So if either of them is null, we can just return the other one. So if T1 or T2 is null, just return the other one. So merging corresponds to, we have T1 and T2, and we would like to create the larger tree T that first contains T1 and then T2. So if we are talking about sequences, this just corresponds to concatenating the sequence here and the sequence here. So 1, 2, 5, and 3, 2, 1 will get concatenated into 1, 2, 5, 3, 2, 1. And if we're talking about binary search trees, there is additional restriction that every key in T1 has to be less than every key in T2. So the maximum key on the left is less than the minimum key on the right. So in this, after this, we can concatenate them in the same tree, so that first we'll have all keys from T1, then all keys from T2. Return another one that's not null. So then, how does merge work? Well, we have to look at what's in the root here and what's in the root here, and we'll take the one with minimum 1, right? So whichever one of them has less priority, well, usually the root is the one with the minimum priority, like the might be not that self-evident, but the heap property requires that the root has the minimum value. So the X is binary search tree property and Y is a heap property, where the root has the minimum value. Return the other one, and so if T1 Y is less than T2 Y, well, what do we do? So if this Y in T1 is less than the other one, well, we have two different subtrees here. So this has to be root. So we'll merge these two, and we'll make this the left subtree, the right subtree of the Y1, of the root of T1, and the other way around. So if Y2 is smaller than Y2, then the second subtree second tree has two subtrees, and there is T1. We'll merge the left child of the second subtree with T1 and make that the new left child. So here I'll make the recursive call. So it's merge T1 right and T2. And now I want to replace T1 right with this result. Well, I cannot just say that T1 that the right child should be this, because my goal is to make all fields immutable, since it's easier for me to implement and I don't want to change any values. And this result, instead, we create a new node where the left child is the same as the left child of T1, so the same one that was there before, and the right child is the result of this merge. So I return the new node. As usual in persistent data structure operations, especially on trees, I want to return the new node that was created by all of the operations that I have. So return new node where the left child is T1 left, and the right child is this result. Well, maybe I have some other operations. So for example, maybe I use this Cartesian tree to calculate sums on segments. So this way I have to recalculate the value of the sum in this new node. And the other branch is pretty much the same, right? So I do merge of T1 and T2 left, and I return the new node that I got by getting two subtrees, right? So by concatenating this subtree and this subtree. Well, there is some value here, Right? So T1, that value also has to be somewhere here. Because in Cartesian trees, we usually don't store the information only in leaves, like in segment tree, but all the intermediate nodes also store some information too. Otherwise, we do merge of T1 and T2 left, and then we do the same. So this is the persistent tree, and well, the split is pretty much the same, right? So whenever we are going to modify either the left child or the right child, we're going to create a new node. So the Cartesian tree or tree is mostly used not for online problems. So usually if you have online problems, it's easier to solve with a segment tree, but by fact that split doesn't destroy the original tree. So if you are working with a normal tree, which is not the persistent one, when you make split, the original tree is destroyed, right? So if you want to split an array 1, 2, 3, 4, 5, 6 into, let's say, three parts by 2 splits, now you have 3 trips, 1, 2, 3, 4, and 5, 6, and you don't have the original from 1 to 6. But if you use persistent ones, you still have the pointer to the root that corresponds to this tree, and you have 3 new ones. And that's the advantage that you have to use when you use persistent trees. Now, for example, you cannot do this kind of operation from using just normal trees. So, for example, you want to operation, so you store your array as a sequence in implicit tree, and you would like to do all values from x to L. Well, basically like this. So for I from 0 to L, a x plus I set to be equal to y plus I. So basically, you want to take an array, you want to take some part of this array and copy it into another place. Well, you cannot do that with normal trees, right? So because with normal trees, like if you were going to do that as like make this split, take this part, make this split, and replace this part with this, well, when you are going to cut this part of the array, the left half doesn't exist anymore. Right? So each node of normal tree is only present in one tree. So after you make some split, the original array does not exist anymore. It is destroyed, and now you have two arrays. For example, this you have 1, 2, and 3, 4, 5, 6. Well, since we're working with persistent ones, and the segment tree that we work with and this tree are fully persistent ones, so you can modify and access any version from the past. So if you'd like to copy one part of the array into the other place, you can do that with persistent trees. Since when you cut this part from the array, the original array still exists. So to do this, you can just take your initial array, you can cut this part from x to x plus L. Now you have still your original array A, and your part from x to x plus L. So this is, we have this part of the array. And now you can insert it anywhere you want. So for example, you can split your array here. You can get two parts from 0 to y. Then you can have this part from x to x plus L. Then you can have the remaining part of the array from a y plus 1 to the end. Now you can see that we've increased the length of the array, and some elements are present more than once. Sadly, well, while this is a cool operation that we can have, this introduces one more problem that we need to solve. Let's look at the following code. So initially, we create some node, and new node with some values 1, x is equal to 1, and priority is equal to 2. You should really use random priorities, but just to illustrate that the priority is constant for this node. So whenever we create a node, usually whenever you create a node, a new priority is assigned to that node. So you'll have some constant priority here. And let's look at the following code. So node root will be initially null. And then some number of times we will merge root, we will merge the current root with this node n. From 0 to x, we'll set root to be merged with n. So basically this means that if we look at it as a sequence, then we're just appending the same value to the end. Right? So we have initially an empty array, then we append 1, then we append 1 again, and so we do that x plus 1 times. So how do you think the tree looks for this work? How do you think the tree looks for this operation? Well, priorities are not random anymore. Right? So all the nodes in this tree, there are n nodes, and they all have the same priority, which is a problem, since our runtime depends, since the depth is log n, only when priorities are random. And when all the priorities are the same, well, depending on how you break ties in your code, your tree might be either branching left or branching right. So if all priorities are the same, and you probably break ties the same, well, in your code, probably you break ties in case you have equal priorities the same every time, so your tree must be left-leaning all the time. And that's the problem. Since we have a tree, and we expect that the depth of the tree will be log n, but it's not. It's linear. Okay, so now we will get rid of priorities, and we will describe what's called the randomized binary search tree. And like, it's a funny story because usually we started our description of trips by them having keys and priorities. Then we got rid of keys. Now we're going to get rid of priorities. So this is usually shortened as RBST, Randomized Binary Search Tree. RBST. And we get rid of priorities, but instead we'll do some more calls to the random generator. So what I want to do is, well, first let's look at split operation. So split operation doesn't look at priorities at all. It only looks either at keys or at the values or at the subtree sizes, and doesn't do anything with priorities. So split remains the same. But merge does. So as we saw, we compared two different priorities. So if T1 y is less than T2 y, we had one branch of this if statement, and if the second tree was smaller, then we had some other operation. Similar but different. So what is the probability that this happens? So we have T1, a tree, and we have a T2. So if all of our priorities were random, what is the probability that this value here, y1, is less than this value here, y2? Well, we can look at this as we've chosen size of T1 plus size of T2 random values. And the fact that and y1 is mean of the first, size of T1 values, and y2 is the minimum of the last size of T2 values. So, and we would like to compare the minimum of the first T1 and of the last T2 values. Well, what's the probability that y1 is less than y2? This means that the global minimum among all these T1 plus T2 values is in the first part. So probability that y1 is less than y2 is the same as global minimum is among the first T1 values. And the probability of that is easy to calculate. So what is this probability? Yes, so the minimum, if those are random values, then the minimum is likely to occur at any positions equally likely. So then the probability that it occurs on the first T1 positions is, well, how many positions are there divided by how many positions are there in the entire array. So it's T1 divided by T2 plus T1. So we can replace this check with the following one. So if random value from 0 to 1 is less than T1 divided by T1 plus T2, then we'll make the first tree, well, the root of the first tree, the root of the merged one, and otherwise we make the other tree the root. Make T1 the root, otherwise make T2. So that's it. So the only thing we need to replace is how we decide which of the vertices should be the root of the merged tree. Now we do it like this, and well, it's better to deal with integer random since, like, first of all, using rand like this is not advised, right? So, like, since URL coding is C++, you should use like uniform distributions and normal and good random generators, as opposed to just standard rand function, which fails in surprising ways. So we can rewrite it like this. So random from 0 to T1 plus T2 minus 1. So we choose a value, an integer value here, randomly from 0 to T1 plus T2 minus 1. If it's less than T1, then basically we've chosen a value in the first part, then we make the first tree the root, otherwise we've chosen the second tree. Okay, so this allows us to merge the tree with itself, basically. Now, let's modify this code a little bit. Instead of merging root with n, I will merge n with itself. This basically corresponds to me doubling the array each time. So in the beginning I have just 1, after that I'll have 2 1s, after that I'll have 4 1s, and so on. So I can repeat this array. So basically I can create a tree containing 2 to the power of n nodes in polynomial time. Well, this will not be a tree, exactly. This will be more like a directed graph. So a lot of every node of this merged tree that has size 2 to the power of x plus 1 here, each node will be referred to multiple times. So this is not a tree, this will be more of a undirected graph. So this will look like this. So we have 1, 1, something like this. 1, this refers here, and the left part is here. So this might be the subtree of size. This is a tree of size 4, right? So we have a root. Its left subtree has size 1, and its right subtree has size 2. So the total tree has size 4, and so on. After we can draw the same tree. And we can merge it with itself. And we get something like this. So this now points here. This now points somewhere else, and so on. So this is the left subtree. There must be somewhere right subtree. This points here. Like the right subtree is this, and the left subtree is this. Something like this. It's fun to think about what happens when you try to merge a tree with itself. Okay, and as I said, this tree, well, this persistent RBST now, is mostly used for these operations like copy this part of the array into some another part without destroying the original array. So the code like this, which was here before, let me repeat it. Can be done with, if some values duplicate, so if after this assignment some values will appear in the array more than once, then you'll have to use persistent trips, because in normal trips, each node exists in only one subtree at any moment in time, since if you split an array, it's permanently destroyed. Well, you can merge it back, but then you didn't get any new information. So, if you need to do such an operation where some values are duplicated, it's a strong hint that you need to use randomized BSTs or persistent Cartesian trees. Okay, and the last thing I would like to talk about is dealing with memory. So, as I said, you usually only keep the last version of the persistent Cartesian tree. So you usually use it to store a sequence with this kind of operations, and still the memory overhead is very large. Well, usually, as I said, the memory is the bottleneck in persistent data structures, and especially with trips, since they have a larger constant factor, and well, you can sometimes not fit into time limits. What you can do with, well, you pretty much cannot do anything with segment trees, since usually you need all the versions before, but you can do something with Cartesian trees, and you can rebuild a tree every X queries. So after every X queries, basically you free all the memory that you've allocated so far. To do that, you probably need your own allocation. So for example, you can pre-allocate the large array of nodes, size, let's say 10 million. And instead of creating a new node, which is, by the way, a more expensive operation than just increasing the pointer and taking the next node in this array, you can just store nodes here. You can pre-allocate the large chunk of memory before you run all the expensive operations. Allocating the memory is faster this way, and you can free the memory easier, right? So to free this memory, you need to run DFS. DFS from current root. So since we're storing the sequence, it's probably we get an array of lengths n. Then that's the first part. The second part is we just delete all the memory that we've allocated before. So we delete all nodes, and then we build a new trip from scratch. We can even build a perfectly balanced trip, so our operations on it will be faster for some time. So, if we choose x to be about q divided by log q, so if we rebuild and q is the number of queries or the length of the array, could mean both of these. So, if we rebuild every q divided by log q operations, this means that we will have about log q rebuilds. Each one works in linear time. So we just run the DFS, then delete all nodes. This is done in constant time, and we rebuild. So the total time to rebuild all the trees is q log q. But the maximum memory is max memory is less than or equal to, well, x, since we rebuild after every x operations. So it's n plus x times log n. Right? Each operation gives us about log n memory overhead. So, and x is about q divided by log q, so it's linear. Here I use n equal to q. So I assume that the length of the array and the number of queries on this array are similar. So here, how we get linear memory, so we don't get blown up to n log n memory, and still we maintain q log q runtime. And of course, you can make a trade-off. So you can make this a little bit larger, so you get more memory usage, but you do less rebuilds. So you have less time but more memory, or you can do rebuilds more frequently. This way you get more rebuilds but less memory, and so on. And the last tip to optimize trips is, well, do we need all those structures? Well, we can replace those just by ints. So a pointer is basically an int. So we can just, instead of having a structure, which is more convenient, but if you're trying to optimize and to squeeze into time limit every bit of time and space optimization matters. So instead of node will store ints, and we can have int left, 10 million right, 10 million, I don't know, size, also 10 million, and so on. So basically we unpack all of our structures into different arrays. Well, using structs might be better because like accessing random places in different large int arrays can be expensive. But if you're trying to optimize for space, this might be better since we are not going to use pointers, which are 8 bytes, but instead you will use just ints, which are 4 bytes. And so, like, each node of the tree is just represented by one int. And to know the fields of this node, you can just access all these different arrays by that index. I've done that because, like, as I said, I was coding in Java, and in Java classes and structures are more expensive than in C++, so sometimes that was a required optimization, but I've seen the C++ programs that also did that. Okay, so that's it for persistent data structures. Today we have a normal contest from Petrozavodsk winter camp from 3 years ago. This is going to be a hard contest, so brace yourselves. Yeah. Okay, so any questions relevant to this lecture or maybe not? Yes? Sorry? Yes, you cannot do that if you rebuild the tree. But usually in problems involving persistent trees, you only use it for like non-destroying operations, and you basically only storing the latest version of the tree. You don't need all the previous versions, you only use it for non-destroying splits and non-destroying merges, which is why you can rebuild, since you are only caring about the latest version of the array. Okay, any more? Okay, so now we're done with our lecture. Thank you. And I'll have a couple announcements right now. So, first of all, we are going to take a photo on the stairs outside the IC altogether. And second of all, I want to ask you to bring a copy of your student ID or of your passport tomorrow. There is a program that my university runs, and I would be very grateful if you could fill in those forms. If you were there last year, Andrew at Andrew's week, he also did similar thing like that. So this basically teaching foreign students helps our university look better in the eyes of the ratings and the government. So I would really appreciate if you could fill in some of those forms. They will be here tomorrow during the lecture, and you will need a copy of your student ID or your passport, or basically any ID that you have. Okay, thank you.
Could you give us at least not the entire solution,